It's 10 o'clock, so we can start with this fifth NERO Network Webinar Café. Good morning, everybody. My name is Valentina Bacciu, and I'm a researcher at the National Research Council of Italy. And today I will moderate this webinar that will focus on understanding fuel characteristics and their role in fire behavior, a scientific practical approach to extreme fire events. Our speakers today are Paulo Fernandes from the University of Trás-os-Montes and Alto Douro in Portugal, and José Luis Soriano, the head of Fire Analysis Unit at the Generalitat Valenciana in Spain. So, as you can see, we will start from the scientific approach, and after that, we will understand how we can apply this concept also in practice. This meeting will be recorded and also shared later on in the YouTube channel of the NERO project. And at the end, we will have also a space for question and answer. So please, you can write your question in the chat about the team, any curiosity you should have, and we will at the end pose this question to our speaker. First of all, before presenting you, before starting with the webinar, I would like to introduce the project under which this webinar cafe is organized. NERO, which stands for European Network on Extreme Fire Behavior, is a cost action. So a bottom-up and interdisciplinary network with a duration of 4 years that boosts research, innovation, and career. NERO started in October 23, and we are now entering in its second year. And at this link, here, you can have more information about the project and have also a look about our objectives, first results, and also stay updated on all the different activities. So the aim of the project is to address the extreme wildfire challenges by bridging together researcher and practitioner in order to advance the current state of the sciences, thus making a crucial step in improving fire management, firefighter training and safety, and also public safety planning. So the vision of the project is to break the silos between these two group of stakeholder, let's say, to open up new avenues of research in extreme wildfire and bridging the gap between these two groups, science and practice, in order also to enhance the operational capacity at the European level, and we hope also beyond. So some figures in order to give you the whole picture of the project. The NERO so 32 countries are participating in this project, represented by more than 175 participants, of which 21 are practitioners and 26 are women. And yes, we have to do better in this field. The work in NERO is divided in 4 working groups. Working group 1, historical extreme. Sorry, there is a. Can you turn off your mic? Thanks. So Working Group 1, historical extreme wildfire. We are collecting data related to complex wildfire, and with the aim to create a public database on fire progressions data that will be used then in Working Group 2, where we analyze this data in order to generate content that can transform raw data into actionable insight. The goal is to turn on this information into practical tools that can be used for supporting decision making and improving wildfire management strategies. Then, in Working Group 3, capacity building, we will open new pathway for indeed capacity building and improved firefighter training and safety across Europe. And last but not least, Working Group 4 is about communication and outreach, and here we are focusing on maximizing the impact of the project in order to and also guarantee the network sustainability through effective communication and outreach activities. So, okay, in particular, the NERO Network Café webinar series is part of Working Group 3. These webinars indeed are aimed, let's say, serve as a platform for dialogue, bridging together expert, practitioner, researcher in order to discuss key issue, share new insights, explore new solutions, and also discuss the applicability of this novel research for wildfire management. You can have at this link, you can have more info on the next webinar that we are organizing. Then, furthermore, one of the main instruments that NERO can offer you that I would like to mention is represented by different types of grant that are here summarized. Indeed, NERO can offer funding for in-person exchange visit, also virtual exchange visit, conference participation. All these grants are aimed at the achievement of NERO research and capacity building also objectives. So all these grant needs to fit with the scope of the work planned in each working group. In order also to further fuel the relationship between researcher and practitioner. Again, if you want to have more information concerning what NERO can offer you, please visit this web page or write me because as a grant awarding coordinator, I can also provide you information concerning this possibility. Furthermore, let me add that in January we are going to organize an online assembly with all the network, so with all the participants at this network, in order to present the work plan for year 2. So this meeting, this online meeting, will allow all the members to be aware of the objective for this second year, what are the initiative to be expected, and also we hope to express their interest in launch new initiative within the scope of the project. Okay. Then, without further ado, I would like to present our speaker today. So the first one is Paulo Fernandes, Associate Professor at the University of Trás-os-Montes and Alto Douro in Portugal. Paulo is very well known. He's a long research career in fire behavior, ecology, fire management. focusing also on prescribed burning for hazard reduction. He contributed significantly to many reports. The very recent one are the UNEP spreading like wildfire in the state of wildfire 2023-2024. And his research interests include the interaction between fuel, vegetation, and weather in determining fire behavior and its effect. So today he will talk about the effect of structural fuel characteristic on fire behavior. So we will learn, we will understand what do we know about fuel type and fire behavior relationship, and also the role of fuel in extreme fire behavior. The second speaker is, as I already said, José Luis Soriano. He's a forestry technical engineer, head of the fire analysis unit at the Generalitat Valenciana in Spain. He also has extensive experience in wildfire analysis, training, international cooperation and collaboration. He participated in several wildfire management projects, including those in Guatemala and Spain. Today, his presentation will focus on monitoring fuel moisture and its relation with fire behavior. And this activity was developed in collaboration with the university. So I will stop. Oh, sorry, I was forgetting, this is very important. At the end, we will have a 30-minute of question and answer session. So I'll invite you to participate in this activity. And this will further help in bridging science and practice in wildfire management. So please, if you have curiosity, questions, please write down in the chat, and at the end, I will read them and post them to our speaker. So this is the very last slide from my side, and I leave the floor to Paulo Fernandes.
Good morning, all. Thank
Good
you,
morning.
Valentina, and thanks for the invitation. Let's see if I can share. Something it's not right. It doesn't seem to be reacting.
No, we cannot see your screen.
Okay, maybe I will go out and re-enter again, because it seems to be frozen on my side.
Okay. Okay, sorry everyone for the for the technical issues. Let's see if Paolo can share his screen. Otherwise, he can also send us his presentation and we can share from Sardinia, let's say. Okay, Paula, I can see you. Okay. Now I can see the screen. Your screen,
Okay.
but not your presentation yet.
So to go to the presentation, you see it now?
No, I think that when you start sharing your screen, you should identify the different screen that you have. There is one screen for example, the presentation, PowerPoint, one for the computer screen. No.
Because it only says share window or share screen.
Try to share the window. No. Again, we can see only your screen. But maybe you can. Where is your PowerPoint presentation? Paolo, if you want, we can you can either send me the presentation or we can move to José Luis.
Acho que só estamos.
Fabio, if you want, we can you can also send me the presentation. Because I'm sorry to to leave all these people.
I'm trying a different way.
Mhm.
Because I was doing this.
Paolo, I cannot hear you anymore. Fabio, sorry, can we?
Yeah, Valentina, Paolo is changing for the app. So yeah, maybe we can share this way. If not, maybe we can start with José Luis Soriano, but maybe in 1 minute, Paulo will try to connect with the app and try to share this
Okay.
way.
Okay,
Because
so
until now, Paulo is trying to share with into the browser.
okay, gotcha.
Had some difficulties.
Mhm.
So if we cannot
So-
to work this way, maybe we can start with José Luis Soriano.
Yes, okay. Okay, let's see if oh, fantastic. Now it's working.
Finally.
So,
Try to put in presentation mode, Paulo.
you can, yeah, please.
Yes, the problem is that I was doing on the web and not using the app. So, okay.
Now is perfect. So, please, Paolo, the floor the floor is yours.
Sorry for the delay and confusion. So I will be speaking a bit about how can we understand fuel characteristics and their role and effect in fire behavior characteristics using different approaches. So first of all, some things about fuel description, the role of fuel, and I will separate in terms of fire movement and fire energy. Then some work, experimental work about the effects of fuel in fire spread, both from lab experiments and field experiments. Then I will move to speaking a bit about the issues, which are many, and the challenges of trying to assess how fuels affect wildfire behavior. And finally, some information about how extreme fire behavior varies with fuel type. Okay, the most basic thing, what is fuel? Sometimes there's confusion about this because we have biomass, but not all biomass is fuel. And we have this potential fuel, but only part of it will be available to be burned in a given fire in any given moment. And so what fraction of the biomass is fuel mostly depends on its size and on its condition, whether it's dead or live. And available fuel is mostly controlled by its moisture content, but also by fire intensity and position of the fuel. And we can say in broad terms that the nature of a fire is defined by the nature of the fuel, and I will get back to this afterwards. Fuels are complicated, especially for people not, let's say, not initiated in these things. So there's a hierarchy. There are some ways of organization. So we have full particles. Full particles have intrinsic properties that normally we do not consider, especially for the most practical applications. So these are properties that influence combustion, but they are implicit. And so we don't really need to be very much concerned with describing them. The most important full particles properties, those that relate to size and shape, surface area to volume ratio, particle density, mineral content, volatile content, heat content. So some physical, some chemical. Then all these particles come together or are organized together in layers. And so a given layer has some distribution of particles by size class, has a given depth or height, a certain load, the amount per unit area, a certain arrangement in terms of porosity, compactness, bulk density, which is the amount per unit volume, and some proportion of live fuels in relation to dead fuel load or in relation to total fuel load. A fuel layer, it's considered to have extrinsic properties. So these are the properties that we can try to relate with observed fire behavior. And then we have a fuel complex. A fuel complex can be just one layer if you only have one layer, but very often we have at least two layers, and then we can try to categorize these fuel complexes, varieties as a full model. If we use the Quatermael's based fire spread models and applications, a full model is for surface fuels. And if we work more at the stand level organization, normally we describe these as a full type. And so a full type will consider not just surface fuels, also the ladder fuels or transition fuels and the canopy or crown fuels in the trees. So it's more a matter of composition, physiognomy, and continuity in this way of describing fuels. And so for any given place, we can describe what fuels are there, both in qualitative terms and in quantitative terms. Here it's an example, a pine forest in Portugal. You can see it has some amount of shrubs. Shrubs have a live component and a dead component. It has a canopy or a crown layer, which is a bit distant from the ground. Surface fuels are composed, in this case, of a shrub layer, a litter layer. Then you can see the distance, average distance from the top of these surface fuels and the canopy base height, which is important for crown fire development. We can also describe canopy density or canopy bulk density. You look at the fuels on the surface, you see there's some variety of diameters or thicknesses, so we can classify them by size classes, which feeds the fire spread model of Quatermael. And then doing sampling, in this case, a combination of destructive and non-destructive sampling, we quantify the fuel loads by size class and by also live fuels, only fine live fuels, because larger than these are not an input to the model. And so we have 28 tons per hectare of dry weight plus the canopy, which was not assessed in this study. So the nature of the fuel defines the nature of the fire. An example of these in forests, typically forests have a multi-layered fuel structure. So you have litter, shrubs, and a canopy. And so fire needs time in terms of, for example, drying after the last rainfall to develop between fuel layers. And so usually we have low fire intensity at low fire danger levels. Here you have two examples in pine forest, in eucalypt forest, two experimental fires. In shrubland, under more or less the same fire danger or fire weather conditions, it's completely different. So you will have a much more intense fire because shrublands are composed basically of just one layer, which is a canopy. It can be a small canopy, but it's like a surface ground fire. And so you have high fire intensity or even extreme fire intensity at low fire danger levels. Of course, these will change above a certain fire weather threshold, as we will see some minutes after this. Because of these fuel nature, we can represent fires, in this case, fuel models, but it could be the fires burning under certain circumstances in these several ways. For example, in this fire characteristic chart, so you have the North American and FFL standard fuel models represented in terms of rate of spread, heat per unit area, and then fire line intensity and flame length classes. So you can see where these fuels or fuel models are located. And this, of course, it's quite useful for management applications. To understand how fuels affect or determine fire behavior, I will more or less separately address movement and energy. So in terms of movement, we need to understand how does a fire move or how does a fire spread in a fuel layer or in a fuel complex. So fire spreads across the top and progressively down through the fuel, and you have this combustion interface. So this is more or less conceptualization. Phil Cheney in Australia was the first one that tried to provide this concept. And then movement basically of a flame front. So it has a rate of spread. It has these flame front has some geometry, some properties, length, height, angles, depth, all that you see in the photo. And the different fuels, the different fuel layers contribute in different ways to not just to the flame front, but to what happens after the flame front passes through. So the most exposed to ambient conditions, the top of let's say the top of the fuel complex or the layers which are on the top account mostly for rate of spread, flame length, fire line intensity. Then if we move down in the fuel complex, or if we are looking at post-fire combustion, then the fuels there are contributing more to flame depth, to residence time, and coarser fuels and more compact fuels are involved in these. And finally, you have the post-frontal combustion zone with smoldering combustion, something we don't really see in this photo because this is an experimental fire with the duff layer very moist, and so we don't have smoldering combustion. And then we have the residues that stay there, that don't burn. Of course, if you have a canopy and the fire can move from the surface to the trees, you will have a crown fire, and then another full layer is contributing. The question of energy. So energy is perhaps the most easy to address issue in terms of contribution of fuel characteristics, because energy release is proportional to fuel consumption. We know that fuel consumption is a function of the amount of fuel we have and the moisture of it. So here an example of a study showing this, fuel consumption by fuel category as a function of fuel moisture contents, and also the Canadian fire weather codes. And then we have fire line intensity, and fire line intensity is directly proportional to fuel consumption. Fuel consumption in the flaming zone, in the active combustion zone. And so we can just think about the effect of fuel load, as you see in this graph. So fire intensity directly proportional to fuel load, depending on whether the fuels are moister or drier, fire intensity will be lower or higher. So this is the most basic thing, that the one that no one never doubts about the role of fuels in fire behavior. It's the influence of fuel load, but you will see that this influence is not, it's not maintained when we are talking about the rate of spread of the fire. So some results obtained in the lab about the effects of fuel on fire spread rate. First of all, fuel moisture content. Fuel moisture content is always detected, its influence, either in the field or in the lab. Why is it so important? It increases time to ignition. Moisture fuels require more heat to reach the ignition temperature and to sustain combustion. And so fuel moisture content slows down combustion velocity, and you can see the facility of fire propagation. It's governed by this ratio between the amount of fuel that is produced and the amount of fuel that is absorbed. If fuels are moist, of course, heat production is lower, and the demand for it for pre-ignition is higher. So this obviously affects the likelihood of fire spread, whether it's sustainable or not, if fire fronts, for example, are broken or continuous, rate of fire spread, fuel consumption, flame size, and fire line intensity. Examples of this fuel moisture effect obtained in the lab under no wind conditions. So for different assemblages of data, both from our lab, but also combined with information published in other studies. So you see they more or less follow these exponential trends, and they are not very different, at least accessed in the lab. We can try to access the effect of fuel particles, which is quite difficult. As I said before, they are intrinsic, but in this case we succeeded. We use this surface area to mass ratio, which basically it's surface area divided by particle density. So it combines the effects of surface area to volume ratio and particle density. And so you can see some effect of on fire rate of spread in the lab for these highly variable, because here we put together dead fuels, full beds of live fuels, and mixed live and dead fuels. Why does this happen? Because higher surface area to mass ratio implies a large exposed area, which promotes heat transfer from flame contact, and temperature rises faster when mass is low. And we can also see the effect of full height or full depth, which is, at least in the lab, it has a very linear effect on rate of spread. What you see on the epsilon axis, it's always the relative effect. Why does this happen? Because heat transfer is enhanced in deeper fluid beds, because a larger portion of the flame is transferring inner energy to the fuels that are being heated. Now, an example of the effect of bulk density in these mixed live and dead fuels for a fixed wind speed in the experiments. So you see this pronounced bulk density effect. In fact, it's just an indirect effect. It's not really an effect of bulk density, because we found out with these experiments, and they were very comprehensive in terms to trying to get rid of correlation between fuel variables. Spread rate decreases with full load for a given full height. So this, in fact, it's an effect of full height. And other subsequent experiments confirm this. So rate of spread decreases with full load, and it's an important effect. Here, what you see, it's a multiplier. So we multiply this figure by no slope rate of fire spread to calculate rate of spread when we have wind present. And so we know that rate of spread will increase with full depth, but at the same time will decrease with full load. And our experimental setup controlled very well for these two variables. So we were able to separate the effects between each of these variables. So more fuel, this happens basically because if you have more fuel, you are decreasing the effect of wind speed. Field experiments. So we can see the effects of fuels in a given fire. You can observe an experimental fire and try to model or at least document variability in fire characteristics in that fire. This is my very old study in using these very small plots in shrubland. We were able to do that. Basically, we were able to model the effect of full height and to a certain extent also of full moisture. Or in this single high intensity experimental fire in the summer in a pine forest in Portugal, we had 4 different fuel conditions. Mostly, the differences were mostly related with surface fuel load, which varied a lot between these 4 situations. Also a little bit with canopy base height. And so it was very clear in the field that both the qualitative and the quantitative differences between these 4 situations. So in the same fire, these all burned in about half an hour, so constant weather, some fluctuation in wind speed as it's expected. But these were the general patterns. So this is a powerful example that local fuel conditions can dramatically change fire behavior. Field experiments. Now you see different experiments in different fuels, in shrubland, in data from Portugal, generic shrubland fire spread model that includes also the Portuguese data, in maritime pine stands, in blue gum or eucalypt stands. So you see in this case the effect of full moisture, not very different from that observed in the lab. And then some influences of fuel depth and bulk density. So now we are talking about the fuel structure effect on rate of spread. And they can be quite different between fuel types. And basically this has to do with the range of data we are using, and of course the structure itself of the fuel layers. In this case, the bulk density effect that could be modeled, it's basically an inverse correlation with fuel depth. We should be careful in terms of extrapolation. We are talking about observed fire data, experimental fires. So usually what we find out in these fires with this data is that it only applies to these conditions. So we should be careful or we should avoid extrapolation. An example, this model for surface fire in pine forest. We developed the model, we evaluated with independent data. It looks quite good. And then we checked conditions for applicability. So it only applies in this region, relatively high dead, fine, full moisture content, terrain not too much steep, and also wind speeds not low to moderate wind speeds. So mild conditions that will produce low to moderate intensity fires. Then we confirmed this because we checked the performance of this model with wildfire data. And we also found out that this issue is common to empirical models, but it also holds for semi-empirical or physical or semi-physical models like Hottermel's model. So Hottermel's models performance, it's very much constrained by the lab conditions under which it was developed, and this can give us problems. For example, in the particular case of this study, we found out that what we observe in the field and what Hottermel's model was predicting in terms of fuel treatment effectiveness, the conclusions were opposed because Hottermel's model was not developed to access fuel treatments. Now, moving to wildfires, and especially to extreme wildfires. Wildfires are a different thing, of course. Here you see images and data, statistical distribution of this Portuguese data set, rate of spread in experimental fires and rate of spread in reconstructed wildfires. Mostly those wildfires that actually showed some time ago in these sessions. So the difference between rate of spread, it's around 1 to 3 orders of magnitude. And when we try to examine what is the contribution, what is the effect of fuel characteristics to wildfire behavior, this is an enormous challenge. This is an example. So this study in Australia, in a maritime pine plantation, so they had the full characteristics. They call it full codes. They have full loads, also qualitative description, characteristics of the stand. So they could, and then they reconstructed this particular wildfire, and they could match the full characteristics on the ground with fire spread. And finally, they produced this table where they had fire rate of spread and what fuels were burning. So this is a very rare occurrence to be able to have these specific detailed information about fuels. So this is a luxury that we normally or seldom we have in wildfires. But we can resort to some proxies or some data. Normally, the spatial resolution it's not very good, but we have national forest inventory data, and we can calculate, for example, full loads, typical full loads for a given wildfire in a given region. We have full age maps, time since fire. Here you see in a small area the variation in time since fire. And then we have models that transform or express full load as a function of time since the last fire. This is an approach very much used in Australia when they are modeling or simulating or investigating wildfires. And of course, we have these maps for full types and full models. This is a map that every year is updated for Portugal, 30 meters spatial resolution. Of course, it has issues because it is primarily based on land cover. But then there's this app that people are using to do local improvements, and it's updated with wildfires and with forest management. So it's from what I know, elsewhere in Europe, it's probably the most accurate full model map available. Of course, when we look at wildfires burning in these full types or full models, we are mostly looking at the qualitative influence, because we are not really looking at full characteristics in particular. And we should not forget that full characteristics in full models are nominal. They are not the real full on the field. More and more, we have remote sensing products, and this could be a presentation by itself. In the future, it will certainly provide us with very detailed and hopefully accurate information. So far, it's challenging to translate these products into full characteristics. Anyway, we can also deduce the effect of fuels from the studies we do about fire regimes, large fires, large fire growth, burned areas, and so on. Here you have 3 examples. So what these studies tell us is that large fires, first of all, result from fast spreading periods. Fast spreading periods are a product of fire weather, but the amount of area that burns under the weather influence, it's dependent of landscape configuration. So these studies tell us that the size of large fires is constrained by time since fire and all the metrics we can derive from it, full continuity and fragmentation at landscape level, and pyro diversity, so which is more or less the variability or the memory of fire in the landscape in terms of different patches with different fuel loads, different times since fire, different fuel structures. So fuel conditions really affect landscape level fire spread. I did not mention this before. It's just to wrap up the advantages and issues with each approach. So lab experiments are very useful because we are burning under controlled conditions, but not under natural conditions. And lab experiments have scale issues. So not everything that we find in the lab can be directly extrapolated to the field. Field experiments, we are operating under natural conditions. We are capturing implicit variability, and so we do not need to be worried in measuring everything. Scale can be acceptable. It can also be the size of these fires can be quite low, can be larger, but it can be acceptable in terms of reproducing the fire spread phenomena. the problems it has, it's mostly related with correlation between full variables, very difficult or almost impossible sometimes to tell the effects apart. And of course, we are burning in the limited range of burn conditions, and they are costly, these experiments. Finally, wildfires are the most natural. Capture of implicit variability is present. The spatial scale is total, so it cannot get more real than this. But then we have problems of logistics, safety, the data we can gather in terms of both of completeness and reliability, and especially fuels, as I mentioned before. Trying now to talk a bit about the effects on extreme wildfires. So extreme wildfire behavior, and here I'm considering the extreme of the extreme. So according to this definition, non-steady fire spread with rapid changes, and normally we call these blow-up fires, firestorms, conflagrations with erratic behavior. So things that we would like to know, what are the full structure and full load requirements for these fires to happen? For example, do we have full dryness thresholds that allow these fires? We don't really know much about these, although nowadays there are coupled fire atmosphere models that can be used in an experimental environment to examine some of these things. I give you this very old example, 1962. So, and they give this table about the blow-up potential as a function of full load. And so they say that we need at least 15 tons per hectare of full load to have a blow-up fire. So it's not that much. Although they say that to really have a high blow-up potential, we need 16 tons per hectare, more or less 40 tons per hectare. So it's very difficult to trace extreme fire behavior characteristics to full characteristics, but it's easier to do it with full types. So I give you this example from the Global Fire Database, which is a remotely sensed database of fire characteristics. It covers the entire world. So what we are seeing is the 99.9 percentile of fire spread. In terms of fire speed, this is not really the same as rate of spread. This is the rate of spread average across the entire perimeter of a fire in kilometers per day. So we see that some full types stand out. Conifer forests, this is mostly boreal conifer forests, open shrublands, so this is mostly dry or arid shrublands in Australia, and also grasslands, then mixed forests, again mostly in Russia or Canada, and then you have all the other land cover types. So we can consider these very representative because it includes all the fires recorded in the world. Looking at the bonfire database, which is a database we established, which now it has more than 7,000 experimental and wildfires from the world, very many different sources. So if we look at the full types and consider the 19th percentile fire behavior characteristics, we get this plot. So very clearly we see grasslands and open shrublands produce the fastest fires. So this is about 10, 12 kilometers per hour, the 19th percentile. Then we have a kind of an outlier here, the deciduous broadleaf forest. Well, not an outlier, it's the nature of the fuel. So the lowest intensity and slower fires. Another different situation, slash fuels. So very high fuel consumption and not that fast rate of spread, so the woody fuels after forestry operations, but all the other vegetation types are more or less here in this region: eucalypts, different kinds of conifer forests, shrublands, broad evergreen broad-leaved forests like in the Mediterranean. So they are not very far from each other. Not all full types are here. I only plotted we need a minimum of 10 fires available in the data set for a given full type. And we found out that, well, under extreme conditions, fire spread tends to converge. So we can have these different flammability, so different fire behavior potential that we can distinguish and identify and quantify at low to high fire weather or fire danger levels. But then when conditions become extreme, they merge, or at least we are unable to distinguish from field data, from wildfire data. It's important to note that this effect or no effect is not considered by any fire spread model available, except the most recent fire model for eucalypt forest, the VESTA2 fire model. And so this has implications, important implications for operations and management, and for simulation studies, of course. So why we see these under most extreme conditions? Remember how fire spreads from across the top of the fuel down into the deeper layers. So we don't really need that much fuel above ground when everything is very dry and very windy. Then we have in these fires very dense and long distance spotting. We can have area ignition. We have deep flaming because of all those fuels that are left behind the flame front burning, and that can be significant in certain fuel types. Then we can have flame attachment in steep slopes. And finally, when we have flames like you see in this picture, this is one of the fires this year in Portugal, in this case, eucalypt forest. So when you have flames this size, it kind of bridges all the fuel elements and fuel components. And so we can say that flame size overwhelms fuel or overpowers fuel. An interesting example, this is a Scots pine stand in Portugal. Compact liter, short needles produce these very compact liters. These would be a full model 9, so the lowest fire behavior model in the classical US classification. Distance from ground to the canopy, it's quite high. So even under extreme weather, we would say this would burn as a surface fire. It could burn like this.
I think, do you have a video, Paulo?
Yes, it's a video.
Uh,
It did not play.
no, yes, it's playing. It's very slow. I think connection problems.
Okay.
But
so, well, it was so this was a video of a wildfire in a Scots pine stand in Russia. So more flammable because they have this moss layer, which is very flammable. But we certainly wouldn't expect more intense fire than the one you saw in the video. But actually, this pine stand that you see on the left burned like this, so as an active crown fire. So we can find this really surprising fire behavior that we were not expecting, exactly because of the problems or deficiencies in the fire models and this overwhelming of the fuel environment by fire weather. So, of course, getting back to this movement versus energy issue, this doesn't mean that fuels are not important for many things, namely for impacts on ecosystems, impacts on fire suppression ability, socioeconomic impacts. Everything that you see here depends to a certain extent of total energy release. And total energy release is, of course, a function of fuel accumulation. And here I give you examples of these. So studies of how burn severity in fuel treated areas is lower compared with the surrounding wildfire area, and how these areas are more resilient to wildfire, so they will recover better and faster. And so, oh, sorry, I forgot to update this. This really was the last the last slide that I had to show you. Thank you.
Okay, many thanks, Paulo. So I just would like to remember to everyone, if you have question, curiosity, etc., to post to Paulo, please write down it on the chat. And then we will have a question and answer session after the speech of our next speaker, who is José Luis Soriano. I already introduced him to all of you, but I would like to again said that José Luis is a forest technical engineer. He works at the fire analysis unit at Generalitat Valenciana, and his presentation will focus on monitoring fuel moisture and its relationship with fire behavior. So please, José Luis, go ahead.
Hello, good morning for everyone. Are you listening me?
Yes.
Yeah. Okay. Great presentation, Paulo. It's very proud to be here sharing with this webinar with you. We never had an opportunity to stay together, but I'm very proud of you. And thank you for inviting me to stay here with all of you. So can I share my presentation?
Okay. Presentation mode.
Here. Okay.
Perfect.
Can you see it?
Yes.
Yes? Okay.
Mm-hmm.
Okay. First of all, there are many familiar people here, so greeting to them. And now I'm going to tell you where we are. As you said before, I'm the head of the fire analysis unit in Valencia at East Coast in Spain. We have been working with fire for 20 years. And nowadays we are 10 professionals at different science in my team. There are 6 fire analysts, 1 cartograph, 1 meteorologic physics, and 2 field workers. For if there are, okay. Here, if there are anyone who don't know where Valencian region it is, it's here in the coast of Spain, and this is my team. So what's our objectives? What is our objectives as a wildfire analysis unit? Our goals as a fire analysis unit is to try to make a correlation between the factors that affect fire and fire behavior at any given time. So we need to improve our knowledge of those factors because we want to identify the fire risk with a high level of accuracy, and that allows us to anticipate in decision making. In addition, this knowledge could be able to use in prevention action too. We know that our region burns, and this usually happens with extreme wildfire events, as Paulo said before. In this map, you can see in green color the area of the land with forest vegetation, and in the other map in red color, the total area that has burned in the last 30 years. The objective is to know when, where, and how our territory can burn, to be able to anticipate, to be able to establish safety lines, and to define preventive measures for the population, for the public. So, what are the variables that condition fire behavior? Well, as you know, and as Paulo said before too, there are meteorology like temperature, relative humidity, or wind, and in other cases there are the aspect or slope of the terrain, and at the end there are the characteristics of forest fields. If we know this aspect influence the fire, we can define the fire behavior window that relates to and condition the operational window. This operational window is used by firefighters to establish the strategies and tactics, operational opportunities, and to know the boundaries of the fire's potential. Therefore, as a fire analyst, I have to define this operational time when operational actions could be successful, and on the other hand, it's critical to identify when the fire behavior does not allow work and it is time to think about other strategies. So, what is important to know the live field muster content, fire management? Against this background, it's important for us to know all of them. If we look at those images, it can be identified different fire behavior. You can say that the fuel availability is very different in each case, but can we quantify this availability? Can we classify the fuels in levels of availability? These are questions we are asking ourselves to can make the decisions. But first of all, what we know about our fields. Fields can be classified according to the structure, as we said before, as field models, and in the other hand, can be classified according dead and live field moisture content. So, in Valencian region, we did Scott and Burgan fields model adaptations, and nowadays 14 fields models are identified. But we are aware that there are field models that we couldn't identify so good. Therefore, we have data about field structures, and you can see some example of field model in these pictures. Some of the areas grassland, shrubland, or with some pine trees. And if any of you are interested in this topic, I share the link here. You can download the fields models layer and the methodology of that we use to calculate it. We have developed an app to calculate the dead fine field muster content from Rothermel tables methodology, and we have had forecast data from the Harmony model from National Meteorology Agency, which calculates the forecast of dead fine field muster content. And we usually use this for decide if go or no go in a prescribed burn, for example. And what we know about live film moisture content in Valencia. It's the goal of this presentation. If we know the moisture content of the fuel, we know how prone it is to burn and can therefore define the risk of fire. But why do we want to know? We want to know to identify and quantify fuel availability. What factors affect this variability? If the values of live film moisture content are seasonal or annual evolution, so what's the temporal variability of it, and what's the spatial variability too? It's important to know it, and if it does, it depends on the species. So at the end, we want to know what are the values of live film moisture content in Mediterranean area. And another topic that is important, as Paulo said before too, is what's the transfer to live from live to dead fuel and the effects of fire behavior. So to get answer to these questions, 10 years ago, we start collecting samples of some different species of forest vegetation. At the beginning, it was not really organized, but we realized that importance of such data, and step by step, some fixed plots were defined through the region and monthly sums were collected. Initially, we defined 38 plots, but after a few months, we realized that there were not enough people to collect them, so we decided to reduce the number of plots. Then we decided that 20 plots was the optimal number to collect them. And in each plot, we used to collect an average of 6 samples, more or less. However, we also collect samples in fires and prescribed burnings too, to know what happens in there. Over the years, we was studying this data and having an idea of what was matter with live film moisture content. In this period of time, the values of live film moisture content was studied in 2 master theses of Master Fuego, 3 master theses at Polytechnical University of Valencia, and other collaboration studies around Spain with other organizations. And in the end, in 2019, we start to collaborate with university to achieve a specific goal that I will explain in a few minutes. Because of this collaboration, we had to take many samples. As you could see in this picture, in 2020 and 2021 columns, where the number of samples is higher than in the other years. After all these years, after all these years, 291 plots with 42,084 rows of live moisture content data of 52 different species have been recorded in database. We are currently collecting data on 42 plots nowadays, some of them monthly, some weekly, and some during fires or prescribed burn too. In this video, you can see how the examples are taken monthly, and in the small map here, you can see where the plots are located throughout the Valencian region. And what do we know after all of this time taking samples? First of all, well, in the pictures you can see my colleagues taking samples in the field. After weighting them, they put them in a dryer for 24 hours. After that time, they weigh the dried samples and subtracting both values there to calculate live film moisture content, it's put inside the database. Well, if we represent the values in a histogram, we observe that the main values are between 60 and 120%. There are field values higher than 200%, and there are field values lower than 40% too. Most of them are located between 70 and 100%. Thus, with this graph, we can know the distribution of value in our region. From an interspecific study, we know that each species has a different seasonal variability with different maximum, minimum, and mean values. For example, if we look at rosemary, Rosmarinus officinalis here, its values have more variability than those of Quercus coctifera, for example. Or in another case, Pinus salepensis shows no variability over the year. The values are around 100% all year. In another hand, if we look at the values of species, we observe that these values differ according to the location of the plot. For example, here, Erica multiflora has different maximum values depending on the plot. There are here, these are graphic according to different plots, and you can see how variability in different plots. In these maps, we can observe the location plots from the species. Each color of the dots represent a percentile of life moisture content, and note that variability of life of the moisture content in each plot. But we asking us what's the reason of this variability. In these figures, we plot, for example, Rosmarinus percentiles, using data from 2014 to 2023 here on the left, and data from only from 2022 on the right. You can see how the percentiles lines perform differently. We observe that the moisture content is varied depending on the annual climatic conditions. So we here in the next slide, we have two examples showing how weather conditions modify the moisture content. Above, we can see how dry period here with low rainfall causes that moisture content value to drop significantly, in that case in Cistus arida. Below, we can see how above average temperature causes the same effect as before. If we high temperatures, it makes that the value of life moisture content down significantly. In the other case, we study what about remote sensing. That semi-vegetation index correlate with life moisture content values. So there is a lot of research in this topic, and we have studied some of them in a master thesis with successful result, but this result is not good for all of areas and not for all plots. And what is the relationship between moisture and fire? Remember that one of our objectives was to improve our knowledge of the relationship between moisture and fire. So this is the reason why we usually take samples at the boundaries of the burn area and take notes of the fire behavior too. We observed that most of the life moisture content values in the fire were lower than at other times, and most of them were lower than 100% that you see in this graph. Sorry. And another example of this here in this graph, we represent all of the Rosmarinus samples collected in 2022. which is one of the worst years of wildfire here in Valencia region. And you can see the evolution of the moisture content values in that year. And now if we display the values collected in fire, you will see that most of them are lower than this value, the 100%. Moreover, in some of these fires, we collect one of the minimum values of the data set. For example, here in the His fire, we collect 48% content of life and moisture content. That is one of the lower value in our database. You should know that the His fire or Bido fire here too were some of the largest fires in the last 10 years in our region. In relation to this, we try to study the correlation between life and moisture content and fire behavior factors. And we have studied more than 40 fires and conclude that there are no linear correlation, but we have observed that in extreme fire behavior fires, life and moisture content values are usually lower than 100 or 80%. So what are we doing with life and moisture content data in operational aspect? Firstly, we believe that it's crucial to share this data and knowledge with the firefighting community because of the consequence that can define a good fire prevention or suppression strategy and its success in protection the public, the population. So in this regard, we are producing a monthly report of the status of life and moisture content with an in-depth analysis of the fire species, the relationship over weather, and a comparison with the values of the last 12 months. In this link here, you can find this all of this report that we decide to call petrichor. That, as you know, the petrichor is the smell produced when rain falls in dry ground. So we decide to call the petrichor with this nice word. Another report in which we use data from the life field moisture content are the post-fire reports. They describe the development of the fire in relation to factors affecting fire behavior, such as weather, topography, fuels, and fire severity level. We use the life field moisture content to correlate with fire behavior and to define fuel availability. For example, in this post-fire report, we compare the value of moisture content samples obtained near the burn area with historical percentiles from the same species. In this case, the Rosmarino sample value was 58%, which is within the extremely dry percentile. These fires burn more than 11,000 hectares. This is a clear example for us of a high level of fuel availability. As I said before, in this report, we include a severity analysis too, showing the degree of damage to vegetation and its availability to fire, and the map with reconstruction of fire trajectories. All of this is shared in this following link too. You can show it. Another use case is this application I sharing you for the analysis of live fuel moisture values classified in percentiles. It allows us to select a specific meteorological area, that we have 11 different meteorological areas in our region. With a specific, we can select a specific species for a specific period of time. Here, all of the different species, and here in the top we can select different period of time as a month. In this way, we can know the cutoff values of each percentile here in the center, and for each area of the territory, which can be different at different times of the year. Moisture content percentiles are classified as you can see here in the table below as extremely dry, very dry, dry, standard, wet, and extremely wet. So this classification can be used to correlate moisture content with availability in a simple manner. This is another example, and as you can see a selection of rural species for an inland area and a coastal area for the months of May to September. And for example, we can see how the histogram of the data is different, and the cutoff values are also different from this example for the second one. It allows us to use the data in simulation tools for the design of prevention infrastructure adapted to each area of the territory of the region. Another example of the use of the database is to compare the data of a particular sampling point with historical percentiles. This allows us to determine the fuel availability by comparison with historical values. In this example, this select plot has an extremely dry percentile, which can be correlated with a high fire risk, but at the same time, in May from this year, in the north of the region, there are a plot with values, with standard values. So in this area, the fire risk is lower than in this area, for example. Finally, this percentile analysis has been used in calculation of the fire hazard map of the Valencian region using FLAMAP software, which many of you are familiar with. It uses information on the terrain, fuel structure, climatology, from the analysis of data from ERA 5 program of Copernicus, and historical percentile from live fuel moisture content. With all of this, the fire line intensity is calculated and reclassified into hazard values, and getting the map show here in the right. We are preparing a paper on the methodology used for the calculation of this hazard map. So I hope to share with you in a few months. And what's the next step? Can we continue taking samples for a long time? I'm not sure. What it's a challenge. So until now we have point data. But could we have spatial data of live fuel moisture content? We are asking this question for a lot of time, and could we model it to obtain a map and use it to calculate the fire risk in the whole territory? So that's the challenge, to pass from point data to spatial data. To this end, we turned to the university and signed a collaboration agreement with it. And the goal was calculate a model for forecasting the value of the moisture content for the total territory in Valencian region. And we had the collaboration with other companies such as National Meteorology Agency or with funds from national energetic company too. This study started in 2019 with a pilot project from which a research period was launched to reach the implementation phase, and an online viewer in 2024. It will briefly detail this process to finally my presentation. In the model calculation, it was used meteorological data of land characteristics, vegetation index calculated by remote sensing, and life chemistry content data taken in fields. In 2019, a pilot project was carried out, and the first empirical model for shrubland species was obtained for a specific area, a small area in the Valencian region. The result of this study was published in this paper, and I share you the link for this paper. And as I said, the result of this pilot project allow us to think that the modeling of this value of the moisture content, it will be possible. So after that, we began a new study. Our new study was developed between 2020 and 2021 to determine the models for calculating the life chemistry content of shrubland and woodland for the whole area. After a large research of correlation between selected variables, models were obtained for shrubland and woodland, for inland and coastal area, and were also calculated with rosemary data. The results were optimal for the shrubland models, but not at all for the woodland models. I mean that we calculate models using only values for rosemary moisture because we have realized that rosemary is a representative species in our territory, and it picks up environmental challenge very well. So we consider that its status can be extrapolated to the status of the rest of vegetation. And the other models were calculated using a weight average value with from fraction of canopy cover of each species in each plot. Depending on the location, there were different models for inland and coastal area because the research showed that the correlation and variables were different because in coastal we have the influence of the sea, so the results is different from the inland. And this study was published last year in the paper you can see above, and it's also attached the DOI in case of its of interest of you. Subsequently, an investigation was carried out with the aim to define the new model using machine learning random forest algorithm in order to evaluate whether the results improve the previous model. And the paper was published last month too, and I attached the DOI of this paper too. And well, the results was great, and nowadays we are currently in the validation phase of all of this model with very good results, and hope to be able to implement them soon as a public accessible online platform, which the community of firefighters can consult and could know what's the forecast of life chemistry content value. And in this graph, you can see the result we are getting from the different models to the field values in different plots. And it seems a great validation. And for finish, on the other hand, the design and the architecture of the platform to share this information has already been designed, and all the remains is to successful completely the validation progress to upload there the maps for all of territory. Here, this is an example of these results. So in conclusion, we have seen that the live film history content is like a piece of the forest fire puzzle that we need to study and understand what issues can make of it to improve anticipation, and how we pretend to model its calculation in order to set it into forest fire management. And however, we have difficulties such as the existence of different models for shrublands and for trees, and great varieties of species with different spectral response and different of life film history values. So finally, we hope for near future use the live fuel monster content map to be able to determine the fire risk in the whole territory. So thank you for your attention, and I look forward to hearing your questions.
Many thanks, Jose Luis. Very, very interesting. We already have some question in the chat, but I can see that it was for Paulo, and he already answered. And we have also some other question we received during the registration. But I can see, I saw a raised hand, I think. Yes, from Dan. So maybe we can start with the raised hands, if you want. Please, Dan, go ahead. You can open your mic.
Yes, good morning. Hola, Jose Luis. Thank you both for extremely impressive work. As you know, especially the live fuel moisture content is of extreme interest to me. I have two questions coming from the Netherlands. One, what comments can you give about like how difficult is it to set up a sampling network? Like how much money and how much work goes into it? And like your work is based on rosemary that has a very sort of specific domain in Europe. If you would want to get similar work maybe in other regions, do you think setting up a live fuel moisture content observation network would make sense for a country like the Netherlands? That's my first question. And the second one is more or less related. Do you have plans for making your work available outside of Valencia, for example, to the rest of Spain? Thank you.
Thank you, Dan. Hello, how are you? I don't understand the first question. Please, can you repeat me?
Yeah. So, how much? Maybe just the simplest question is, how much money and effort do you think goes into setting up a sampling network? Because you say it's a constraint for you in the future. If somebody here in the Netherlands, in a fire-prone area, wants to set it up, how does he even begin thinking about this?
Okay. Well, as you know, we have to put a lot of effort to take samples in every day, because there are a lot of, or we want to take a lot of samples, because we need to know how moisture content change around our region. So it's really important for us, our politics support, because of the amount of money they want to put on this project, but it's our it's really difficult, because if the goals for politicians change, maybe we couldn't enough money to support this project. So it's the reason what we want to model this value for have the values in a map, and as I explained before. So for answer your question, yes, it's so expensive. We have nowadays 2 person working every day, traveling around our region taking samples. And there are we had to buy our a big dryer for put samples in it, and I noticed that it's not easy for other organizations to have these facilities. No? So in the second question, if we are thinking to extrapolate this for other region, maybe there are. I think that the models that are developed here with the work with university, they are based on a specific data for here and our region, but I think that maybe it can extrapolate to the other region with similar climate. I think that it's the key. For if the climate are similar, maybe the results can be extrapolated, but I'm not sure for others region in North Europe, for example.
Gracias.
Okay, then I can see also Professor Viegas. He raised his hands if you want to intervene.
Okay, thank you very much, Valentina. I would like first to thank both speakers for their presentations. And I have 2 questions. One for Paulo Fernandes. And leading from your conclusion that in extreme fires, the whole of full properties is not so relevant. This is a conclusion that we also found some time ago. My question is, in that case, what is the relevance of developing full models? Let's say so many full models with so many parameters and so costly also to determine their properties for predicting fires. The other question is for José Luis Soriano, and I'd like to thank you also for your presentation. I'm not sure if I got the information about the time of the day when the sampling is made. Is it at the mid of the day? The second question is about when you are sampling so-called live fools, but for example shrub fools, you have also a mixture of dead and fine and live particles there. Do you separate them, or how do you assess these things? And from your results, I also concluded that you have no, let's say, correlations or explanation for the foliage moisture content. Like say, for example, for the foliage of pine trees, live foliage. Do you want to comment on the whole of those values of moisture content of the canopies? Okay, thank you.
Thanks for the question. It's Well, it's a relevant question. Well, full models will be useful under all other circumstances. And users of full models, so people that do fire simulations, including in ongoing wildfire incidents, have ways to tune, to adjust, to calibrate the simulation as they go. So based on the observed, based on their experience or based on observed fire behavior during that fire. So I think that the major issue here is not whether we are, let's say, over-developing or putting too much effort in developing full models. The real question, I think, is more, when will we have fire spread models that account for these variable influence of fuel across the entire fire weather range. So I think that's it. It's the real challenge. And of course, if in the future we are able to do that, so we have more realistic fire models for extreme conditions, then I think the value of describing and classifying fuels will be even more than it's nowadays. Not sure if I if I answered, but I tried.
Thank you very much.
Thank you, Domingos, for your words, and I try to answer your questions. Firstly, the first question, yes, we take note about the time when we take samples, and usually the samples are taken between 10 and 14 hours in the middle of the day. And we usually take measure temperature and relative humidity too, to have this data to related the moisture content with weather conditions. In the other hand, for second questions, we only take live parts of plants. The upper externally live parts of plant, and usually lower than 5 millimeters, according to take the parts of plants similar than 1 hour period of time returns. And for taking samples in trees, those are the most difficult samples that we have taken, because we try to take the samples in the middle of the canopy and in the extremely part of this canopy, only the live part. But taking with other researchers, they said us that maybe we had to separate the leaves from 1 and to 2 years old, but nowadays we are sampling it together.
Luis, there is let's say a suggestions from Akli Ben Ali in the chat as a question, let's say, concerning also the sampling cost, the question about the sampling cost. If you try to reduce the number of sampling sites by doing a correlation analysis of live fuel moisture content between sites,
Sorry, I don't understand good the questions. Do we
So,
have to reduce?
Akli is present, so if he wants, he can join and intervene. But I think the question is about doing a correlation analysis of the LFMC between the sites in order to understand the relationship and then so reduce the number of sampling sites and reduce the sampling cost.
Okay, so I understand. Well, we are studying and researching how the moisture content vary in our region. So maybe it's a good idea, but what we are viewing or we are knowing is that the values near the coast vary from the values more in inland, no? More inland, or so far from the coast. So maybe in the future we can reduce this sample, putting plots only in the ones in the coast and the other in the inland. But nowadays we prefer to take samples in whole territory to take a lot of data for analysis then.
Okay, thanks. And from I can add also that here at the CNR we developed a network of a fuel stick linked to the weather station. And in the previous year, we connected the results of the fuel sticks with fuel sampling. So it's also an opportunity to reduce at least the effort in sampling, etc. But it's not reducing the whole cost of the network for sure. We have other two questions from that we collected at the beginning during registration, and are two, let's say, general questions that I would like to pose to all of you, to both the speakers. So the first one from Ramesh Glucker is this one. Do you think the role of past human impacts on fuel and fire, for example, traditional indigenous land use practices, are sufficiently understood? And where do you see the research needs? So, Paolo, do you want to answer?
Well, no. Well, it depends, but in Europe, I don't think. Sorry, in Europe, I don't think we had that kind of understanding. There are some studies here and there, but what they characterize is it's the current practice. So what remains from the traditional use of fire. So I'm not sure if that would hold for the past, but in Portugal, where we still have these traditional burning winter fires by shepherds in some mountains of northern Portugal, what we see is that they create this kind of pyrodiverse mosaic. And so actually wildfires there are rare. Most fires are in winter, so or from autumn to spring. They are small, they are low severity, and there are almost no fires in summer. And there are evidence that these summer wildfires, when they enter these areas, they do not spread that much, even under extreme weather. So we have this kind of based on current fire activity. In the past, I'm not sure, but in the past, when we look at old photographs, all we see is rocks and stones on the landscape. So probably the amount of biomass extracted by both people and livestock and fire, of course, was so high that there was not that much to burn on those times.
Thank you, Paolo. I don't know if Jose Luis, do you want to also highlight your perception from the Generalitat de Catalunya?
Well, the question is about the use of fire in traditional manner.
Let's say the role of past human impacts on fuel and fire, if this role is sufficiently understood, and if also this role can be somehow integrated in research needs, let's say.
Yeah. Well, of course, the past role of the human, it's so important to what kind of situation we have in our forestry. What we is showing here is that there are the fuel load is higher than years before, because some of the activities in the land, they are lower than years before, because the population is so major, and the economic activities is lower, or has a lower result. So it has an impact for in the extreme fire behavior, because of this greater fuel load. Instead, in related of use of fire, here in Valencian region, the people used to use fire to reduce the rest of the plants when he is cutting in agricultural activities, but these activities nowadays is decreasing, so it has an impact in the load and fuel load.
Yeah. I think that all the let's say Mediterranean basin is experiencing this situation. We receive another question more more related to your presentation, still from again from Akli Ben Ali. So how can we integrate live fuel moisture content estimates to better estimate fuel consumption and therefore fire line intensity? Is current scientific knowledge good enough to do this? I think the question is for Jose Luis, because he presented, but maybe also Paulo can provide his thoughts on this question.
Yes, maybe Paulo can answer the second part of the questions. Yeah.
Well, we don't really know much about the effects of live fuel moisture content, because, well, we know a lot, or at least something from lab experiments, but this is something that it's really difficult to study in the field, because live fuel moisture content varies slowly. Sometimes it's correlated with that full moisture content. Many times it's correlated with vegetation height. So it's really difficult to access in field experiments, and it's a slow variable. So normally models for full consumption so models for full consumption predict consumption as a whole, not specifically for live fuel, I think, and not normally do not use live fuel moisture content, use dead fuel moisture content. It's true that it's a topic that should be developed. And of course, the effect of live fuel moisture content in fire behavior, we can also find it in the lab, but the current fire spread models do not handle it well. Well, many models don't even use live full moisture content. Rottermel's model use it, but it's just a mathematical extrapolation. So because they only experiment in dead fuels, and then they extrapolated later on, Albini extrapolated the model to live fuels. So it's like a mathematical artifact. And so we don't really know if it works well or not.
Okay, thanks.
Okay, yes, I think I addition some words of that. In our experience, what we using is use the data of live moisture content in a simulation resurgence using Rothermel models, and this model is only for surface. So when we are studying fires with canopy fires, the result of this isn't so good. So Paulo said something about this in his presentation, and that we need to improve how to model or simulate the fire behavior with canopies, and not only in surface fire, because the intensity of this fire is so higher and related to extreme fire behavior is needed for us, for operational firefighters, to know how to calculate or how to simulate this to improve our making decision process.
Okay, thank you both for answering to this question. I don't know if the participant would like to pose other question, but I have one, because especially for Paulo, because you presented in the experimental fire how the different fuel characteristics affect the rate of spread, the fire effects. But if you were to tell a practitioner what are the two main characteristics that they need to pay attention in the field, which would you suggest in the first instance, and why?
Well, it would depend on what tools he or she would be using. I would say full load because of fire intensity, basically, and because of the environmental impacts of full load, including smoke and soil heating and CO2 emissions, all that, and full height or full depth. So if I had to choose two, of course, then you have vegetation type and vertical structure, which are also relevant. but in terms of quantifiable fuel properties, load and depth, I think would be the two more relevant ones.
And do you agree, Jose Luis?
Yes, totally agree. I think that one of the main characteristics of fire behaviors is fire line intensity, because it of it depends the capacity of the firefighters to extinct the fire. So the factors that condition or related to fire line intensity is our goal, no, to the research then.
Many thanks. Because I know that maybe is a easy question, let's say, but indeed, since our objective is to better understand which are the how to translate also our research, our science in practical suggestion, insights for practitioners. I think we need to understand which is very useful for them in the field in order to cope better with the also wildfire or extreme fire. And so what are the main aspects we need to pay attention. So there are no more questions in the chat. And we are almost at the end of this question and answer session. So I would like to thank you, our speaker, very much for your insight, for your presentation. I recall everyone that this presentation, this webinar has been recorded, so everything will be available in our YouTube webpage. If you want to have more information concerning NERO project, you have to type just NERO Network in the browser, and you will find everything, especially on the future activities, on the possibilities, on the grant possibilities. And I just would like everybody for attending, and that's it. Have a great holiday season, and thanks for participating.
Thank you.